different technologies that offer different kinds of latency. And one that we've had a lot of conversations with is coherent technology. And do we want someone to define coherent technology for the audience? Sheldon, you want to give us the short version so that we all can...
Yeah, I live it day to day. So the thing about coherent is if you look how traditional fiber optic networks worked, the way that transceiver technology normally worked is it would just modulate the intensity of light, turn it on and off. And it turns out that if that's all you do with the light, without getting into the deep physics about it here, it's if you have a phenomenon that operates on the optical field over the fiber, and in this case dispersion is one of the main issues there, then it's very difficult to compensate for that in the electrical domain. In other words, people would normally do it right on the optical field using dispersion compensation modules. They could be based on fiber Bragg grading technology, dispersion compensating fiber are the two primary ones. Now what coherent does is there's a couple things that it does for you. And coherent just means using a local, first of all, you're using a laser at the receiver that you're coherently mixing with the received signal. And by doing that, it allows you to recover both essentially amplitude and phase information in that optical field. That's really what it does for you. So what does that translate to? One is certainly better receiver sensitivity, but the big one is you can do all kinds of fancy things now in the electrical domain in terms of how you process that signal. This is where the so-called digital signal processing, DSP, comes in. So you can completely compensate for dispersion. And what's interesting about it is you can do it for dispersion, not just 1,000 or 2,000 picoseconds per nanometer, but 40,000, 50,000 picoseconds per nanometer. You can also do it for polarization mode dispersion. So that's really one of its core features is all of a sudden you can compensate for these optical impairments entirely with electronics. And we know electronics really well, and there's lots of high-scale integration and algorithms, all kinds of neat things you can do in the electrical domain that just isn't possible in the optical domain. So that's really the main benefit behind it.
Let me add my non-technical 5 cents to that piece. And that I mean, if you look, for example, at subsea networks, Bjarni's doing it at Hibernia, and we're doing it at GlobeNet. I mean, you have a glass in the water, and you've got repeaters amplifying signals. And at the end of the day, it's not like you can do a truck roll like you do in a terrestrial network. You build a network for 25 years, and hopefully you'll never have to lift it, right? And if you look at a terrestrial network, many people build fiber infrastructures with 296 count or more fiber pairs. In subsea, we have 4, right? And you're managing terabits of data through those 4 fiber pairs. And so what you want to do is you want to try to squeeze the most amount of, imagine that a fiber pair is like a freeway, and then you have X number of freeway lanes. How many big trucks can I put on that freeway? That's what you're really doing. And that's where coherent technology comes in. We're deploying a network with advanced coherent technology. And so what that allows us to do is to have 100 gig waves, 100 by 100, 150 by 100, over a fiber pair. So what does that really mean to companies like ourselves is basically you can just squeeze more wavelengths inside of your infrastructure. So where before maybe I had a 10 gig wave, tomorrow I can put a 100 gig wave. Or if you look at the cable system that we have between Bermuda and the United States, it was designed for 5 gigs in 1997. And we've been able to squeeze out a terabit out of that cable system over the last, let's say, 12 or so years, right? So indirectly what this means is that you're adding life to your infrastructure by being able to put more wavelengths into, let's say, into the system. The added benefit, of course, of using some of these technologies is that if they're well done, it improves latency. But the real benefit, let's say, to us in the subsea world is not as much the latency as the fact that I can get a lot more out of my network. And that's where we see.
So the networks are similarly GlobeNet and Hibernia. They are designed for 10G technology, and what the coherent allows is it allows for introduction of 40G and 100G waves on the same plant without having to replace the repeaters that are lying on the ocean bed, which you never would do. We have 280 repeaters every 50 kilometers. So you don't touch those, or not would you don't. Hope you never have to touch those. So that's what it allows for. It allows for loads and loads and loads of more capacity on the same submarine infrastructure. If we hadn't, or if the vendors, the equipment vendors hadn't come up with the technology, we would probably have to, we've had to build new submarine cables some time ago, at the cost of $200 or $300 million per. So all the global infrastructure, especially for the internet, and all the benefits that we enjoy, the cheap benefits that we enjoy by video over internet and all that would be way more expensive now. So that's what it does. But however, what it does, talking about the latency, as I understand it, being non-technical, so Sheldon, you'll keep me on track here. What it does is it actually encompasses and has the DCM, so the dispersion compensation module, or the effect, the forward direct correction. Jim, that was good, right? It has it built in, so all that actually does or can introduce latency. So it's a trade-off there. So you might not always want to, when you're servicing the financial customers, you might not always want to deploy this technology. You might want to deploy 10G technology when you're actually servicing the absolutely lowest latency customers. Oops, I spelled out a trade secret.
Maybe I can just add to what Bjarni was saying there. So just so for everyone to know, the standard way people have done dispersion compensation for many years was using dispersion compensating fiber. And as a general rule of thumb, you need about, for every 100 kilometers of transmission fiber, about 20 kilometers of DCF. And so what that translates to is for any link, however long it is, with that, you increase your latency by about 20%. That's a lot. So coherent technology allows you to remove that completely. So that's the benefit, because it's doing it all in the electrical domain with essentially no latency, or very, very minimal in the DSP portion. Now, having said that, one thing that's important to understand, because you mentioned 10 gig wavelengths, it is possible to have your cake and eat it too. In other words, you can deploy systems that are compatible with 100 gig coherent technology, gives you all the spectral efficiency and all the wonderful things, but that are also compatible with 10 gig wavelengths. And to be compatible with 10 gig wavelengths, you still need that bulk compensation if you want to use commoditized 10 gig transceivers. So how do you do that? Well, what you can do is don't use DCF. You use next generation so-called bulk compensation technologies. And these would be, for example, based on fiber Bragg ratings, because fiber Bragg ratings are about that big. So that's the latency through that much space. So it's nothing. So you can deploy those and have coherent if you want, have 10 gig if you want, any type of 40 gig if you want, the best of both worlds.
Thank you.